There are many situations in which to fully understand, we need to combine not only linear momentum, but also energy. One of these is when we're trying to categorize different types of collisions. For all collisions, we have conservation of momentum. Therefore, change in P is equal to 0. We can't use this to differentiate the types of collisions. Instead, we have to use energy. And in particular, for collisions, we look at the changing kinetic energy. Now, there are three different types of collisions. First of these is elastic. E-L-A-S-T-I-C. Then there are the inelastic, just meaning not elastic. Now, for convenience, we talk about two different types of inelastic collisions. We have the partial and we have the complete. And the only difference between these is that for the completely inelastic collisions, when the collision is done, the objects involved will be stuck together. That's the only difference. Now, the third type is what we call superelastic, or sometimes they're also called explosive collisions, or sometimes just explosions. Okay, now let's look at the kinetic energy change for each of these types of collisions. Momentum still conserved, but for elastic collisions, we also have conservation of kinetic energy. It doesn't change. But in the inelastic collisions, we lose energy. Kinetic energy is lost, less than 0. Same thing for the completely inelastic, but just as the objects are stuck together, so too is the kinetic energy lost a maximum. For the superelastic, here we actually gain kinetic energy. Change is greater than 0. All right? That's sometimes why we call them explosive. The objects come out with more energy than they went in with. Now let's look at an example problem where we'll use both conservation momentum and the changing kinetic energy to categorize a collision. We'll have an initial configuration, and we'll keep it simple here. Let's have a mass, and say 4 kilograms. And this one will be moving to the right. And let's have it go, say, 3 meters per second. There'll be another mass. For simplicity, I'll let it be 4 kilograms as well. But this one's going to be moving to the left at, say, 2 meters per second. 2. Okay, that's my initial. Now, after the collision, I have my final configuration. Masses are still the same, both 4 kilograms. This one now is moving to the right at some unknown velocity v, which I'm going to find out. And the other mass, well, that'll be now moving to the right, but it's down to 1 meter per second. Now, anytime you're dealing with motion involving vectors, you need to decide which is your positive direction. So, in this case, I'm going to use the standard. To the right is positive. To the left will be negative. Okay, I got what I need. Let's look at conservation momentum. P initial will be equal to P final. In my initial configuration, I got 4 kilograms times positive 3 meters per second. It's positive because the vector is pointing to the right, the positive direction. Then I have plus 4 kilograms, and its velocity is minus 2 meters per second. Minus because it's pointing to the left, the negative direction. And for my final, I have 4 kilograms times v, and I also have 4 kilograms times 1 meter per second, and that's positive because it's now pointing to the right. All right. Notice that everything has the same units. So in my next step, I'm going to just leave them off just for simplicity while I'm doing the math. So I got 12 minus 8 equals 4v plus 4. And you can see when I solve for v, I end up with 0. So the units didn't matter in the end. Final object is not moving. And you may have seen collisions like this involved, say, on a pool table. All right, we know the velocity. We can now decide what type of collision it was, looking at the change in kinetic energy. So, change in kinetic energy means kinetic energy final minus kinetic energy initial. Kinetic energy is a scalar, so now I don't have to worry about directions or positive or minus velocities. It's just 1/2 times the final mass, 4, times its velocity, 1. The other object isn't moving, so that's the only contribution to the final kinetic energy. Now for initial kinetic energy, I got 2 terms, 1/2, 4, 3 squared, plus 1/2 times 4 times 2 squared, 2. And notice I'm subtracting off both those initial components. So again, all my units are the same. I've left them off for convenience. 18 plus 8. And I end up with a final kinetic energy change of minus 24. My units would have been kilogram meter squared per second squared, which of course are the same units as joules. So minus 24 joules. That's my changing kinetic energy. And that lets us categorize the type of collision. The objects weren't stuck together. So we therefore know that this must have been a partially inelastic collision. In other videos, we'll look at other situations where we need to combine linear momentum and energy to fully understand what's going on.